Texas Math Mundo audience, this is my introduction to my instructional series. Graciously, UIL has allowed me to use their old problems in producing instructional videos. The condition is that it remain a free resource for students, and YouTube is free. So here I am, happy to do some instructional videos. I'll be producing them every so often, interwoven with my interviews with state champions and any other interesting news in the UIL world. So I do want to make sure I thank UIL for allowing me to use old problems in this video series. I think it's just going to be very good that I can point to a specific problem from a specific UIL release, and I think it really piques the students' interest. Today I'm going to be talking about bearing problems. So bearing problems show up every so often. Now I'm embarrassed to admit this, but the first few years I ever did bearing problems, I would just try to draw a picture and apply the law of cosines or the law of sines, and then it hit me. It can be done using vectors. And in fact, nowadays, although I'm not going to discuss this on my instruction, you can often just use a program on the calculator to put in the magnitude and put in the bearing. But the thing is, you have to know the math. If you don't know the math, when they throw variations at you, you're going to stumble and get the problem wrong. So programming is not discussed. So if you enjoy this stuff, or you think you could enjoy it, I'm going to ask that you please hit the subscription button and the notification bell. Leave a comment below and smash that like button. Bearing problems right ahead. My name is Saul Cantu, and this is Texas Math Mundo. All right, today we're going to discuss bearing problems, the traditional type of problem. We're going to review variations of bearing problems next week. So for bearing problems, I have to first admit that embarrassingly enough, the first few years I tried to do bearing problems, I would try to draw a picture of a triangle and then apply the law of sines or law of cosines to solve the problem. Then one day I'm doing bearing problems and it hits me. Wait a minute, this is nothing more than a vector problem. So we're going to lay the groundwork first, and then we're going to look at a particular problem. We're going to look at the UIL release in 2016, problem number 40, which is a traditional type of bearing problem. All right, so let's lay the groundwork first. So the groundwork for doing bearing problems is understanding vectors. In Physics 101, you learned that vectors consist of magnitude and direction. So what happens is that you can separate a vector into its vertical component and its horizontal component. Separating it into its horizontal component, notice that you create this triangle, this right triangle, this angle theta, and we already have the magnitude and we have theta, and so the horizontal component, the x component, is nothing more than, if you look at the cosine of theta, it's the adjacent over the hypotenuse. So the horizontal component can be written as r cosine theta, and similarly the vertical component of your vectors can be considered y equals r sine theta. With this in mind, if you have a typical sort of bearing problem, you go from point A to point B. So you go from point A to point B, and then from point B to point C. And often the traditional type of problem will ask you, how far is point A from point C? And what happens is that you'll break up the vectors into their component vectors. So right here, this first vector, you has this x component and this y component. And then the second vector has this component, the horizontal component, so I can add this component here. And then it has another y component right here, a little y component. And so what you end up having is you end up having a right triangle, where the sides are simply the sum of the x components of the two vectors. The horizontal component is the sum of the horizontal components of the vectors, and the vertical component is the sum of the vertical components of the vectors. And what you end up with is the distance between A to B is equal to the square root. This is nothing more than a application of Pythagorean theorem. It's the square root of the sum of the x components, so r sub 1 cosine theta sub 1 plus r sub 2 cosine theta sub 2 quantity squared plus, and then you do the same thing for the y components, r sub 1 sine of theta sub 1 plus r sub 2 sine of theta sub 2 quantity squared. And you have the distance. Nothing more than breaking up the vectors into its vertical component and its horizontal component. When you add up the two vertical components, you get the one side of a right triangle. When you add up the two horizontal components, you get another side of the right triangle, and the Pythagorean theorem gives you the distance from A to C. And that's what I call a traditional type vector problem. So let me clear it, and let's do an actual problem. So that's the groundwork. Let's do an actual problem from UIL. And so let me put Control V. And what we have here is we have a problem from 2016. Oops, let me do this. This is UIL 2016 number 40. And graciously, UIL has agreed to allow me to use their problems. So here we go. And the problem reads, Anywhere sails 120 kilometers from someplace to somewhere on a bearing of 240 degrees. Then she sails 80 kilometers from somewhere to no place on a bearing of 100 degrees. How far is no place from someplace? Now, years ago, I looked up the word bearing, and apparently bearing means clockwise from north, or I guess east from north, technically. At least that's the definition that I read. But the truth is, as long as you can stay consistent, you can use any orientation, as long as you stay consistent. Since in trig or modern pre-cal, you usually talk about an angle being counterclockwise from the positive x-axis, you can go ahead and use that. So you draw yourself a rough picture. So a rough picture. So she sails 120 kilometers from someplace to somewhere on a bearing of 240. So the pictures can be hard to draw sometimes. Let's take a look. So if we're going to use counterclockwise from the positive x-axis, she starts at some place and she goes 120 kilometers from someplace on a bearing of 240. So, 90, 180, 270. So she goes something like this. Something like this. And this is 120 kilometers. And then from this place, then she sailed 80 kilometers from somewhere to no place on a bearing of 100 degrees. So 90, 180, and she goes 80 kilometers, 100 degrees, 80 kilometers. And it asks, how far is no place from someplace, from the initial point to the other point? And so this is nothing more than a traditional type of bearing problem. And to get the distance, what you would do is you simply add up the horizontal components of the vectors and add up, and since you're going to square, it's not going to matter that the horizontal component is negative. You'll be squaring it. And add up the vertical components of the vectors, and you get the Pythagorean theorem. So the distance is equal to, and let's get this big old square root here. And we're going to have, the first one was 120 kilometers cosine of 240 plus the second one was 80 kilometers cosine of 100, and that quantity squared, that's one side of your right triangle, plus, and we do the same thing for the y components. You do 120 sine of 240 plus 80 sine of 100, that quantity squared. And that'll give you your answer. So let's plug it into the calculator. Let me go ahead and maximize that calculator. And make sure you're in degree mode. And I happen to be in degree mode. And let's punch it in. So we're going to get the square root. So I'm going to do the blue subfunction and square root of, so blue subfunction, square root. And we're going to get the first parentheses is going to be the sum of the x components, which is 120 cosine 240 and then let me right arrow outside of that parentheses plus 80 cosine of, what was that from? Let's see, cosine of 100 and that entire quantity squared. So let me get squared, and then we're going to add the vertical components, parentheses, and it's going to be 120 sine of 240. Oops. And then plus, that was 80 sine of 100. Good. And then right arrow and square that quantity and push enter. And we end up with that, which if we want an approximation mode, is 78.0509. And how far is no place from someplace? 78 kilometers. So once again, bearing problems can be easily done if viewed from a perspective of vectors. You simply add up the horizontal components, add up the vertical components, they create a right triangle, and apply the Pythagorean theorem. This is a traditional vector problem. I hope you enjoyed that. So next week, I plan to produce a video on variations of your traditional bearing type problems. Like you have to know the math, because if they throw a curveball at you, knowing the math will enable you to deal with it. So next week we'll look at variations to bearing problems. Please, I'm going to ask that if you enjoy this content, please hit the subscription button and the notification bell. Also, leave a comment below. Show us what you think about the problems, or if you know any shortcuts, or you know any enhancements to the discussion. Go ahead, talk about it below and leave a comment. Also, smash that like button. I just want to say I really appreciate your support. Thank you very much. My name is Saul Cantu, and this is Texas Math Mundo.